Hello, I am Aditya Arya, and today I'm presenting a video walkthrough of one of my projects where I made system level trade-offs and decisions. So I chose to showcase StrataKV because it's the project where I made the deepest architectural and system level decisions. It pushed me beyond the framework development into durability, so storage, engine trade-offs, crash recovery, system design, and performance analytics. So this is the overall structure of the project. The project is organized into separate engine, storage, MemTable, and server layers. I intentionally separated persistence in memory state management, compaction logic, and transport APIs to keep the architectural modular. The db.go is this is the db.go. One of the key architectural decision was using append-only writes instead of in-place updates. So in the put, as you can see, so first we are appending this. As you can see, the WAL entry is happening before the memtable put, means memtable write. So every write first goes through the WAL, means write ahead log before the memtable, means memory table update. I choose this ordering because if the process crashes after a memory mutation but before persistence, data would be lost. So these would keep in mind, like wall entry is happening first and then the memory putting into the memory is happening in the uh, next part. Also, like wall.go has file.synchronous. So every uh, the trade-off is that here the trade-off is that synchronous fsync calls significantly reduces the throughput because this, as you can look, it is a synchronous in nature, so it especially reduces in windows ntfs because we will see this in benchmarking. Next, the memtable.go, here I have used hashmap data structure. The memtable acts as the native as the active in-memory write buffer. Once the threshold is exceeded, write entries are flushed into immutable segment files. So this is the segment files. You can see it is write segment, read segment, and search segment. I intentionally used immutable segment files because they simplify concurrency and append only persistence, but they also introduce read amplification over time. I have kept the tombstone for the deletion, and it will keep a track of what the files were deleted, and it will keep track of the older segments as well, as they might have some old data in it. And the compaction engine. So another major challenge was read amplification, since the system uses immutable segment files. Repeated overwrites and tombstone can cause segment growth over time and may lead to infinite logs. So here I have used the means here the merging into the memory is happening. So older segment are ensured that they are the first, and then the next segments are inserted. So like the merged data, this is the complete uh, logic of merging the data. Merges fragments, segments, and removes tail historical entries and purges tombstones. Now let's see some benchmarks. So I built a benchmark suite specifically to validate append-only growth, behavior, and compaction trade-offs under heavy overrides. So this includes 50,000 inserts, 2 lakhs overrides, 80,000 deletes, and 8 kilobyte of payload. So the benchmark was, as you can see in the image. So this is the benchmark of these are the deletion operations, and here is the workload time and everything. So during the benchmarking, the workload generated around 1945 segments files and nearly 2 GB of data of append-heavy data. After compaction, the system reclaimed roughly 80% of the disk uses and improved get latency from about 1.35 seconds to 152 milliseconds. So one important thing I learned was that compaction alone doesn't automatically guarantee fast reads. Since the engine still performs linear scans without Bloom filters or sparse indexing, larger merge segments can still become expensive to traverse. That led me to study how production systems like RocksDB and LevelDB reduce read amplification using indexing structures and Bloom filters. So, like I said, this project currently lacks the Bloom filters or sparse indexing, so that's why the get latency is still very slow. Um, let's get to the HTTP HTTP API layer. So after stabilizing the storage engine, I exposed the database through a lightweight HTTP API using Go standard net HTTP pack. Net/HTTP package. I intentionally avoided external frameworks here because I wanted to understand the request lifecycle and transport layer directly. Thank you.